This is the first in a probably quite a long series of videos where I covered the whole of the acids and bases topic at A level, both for Year 12 and Year 13 for AS and A level, because like many things in chemistry, it all runs very nicely from one concept to another. However, I want to start right back at the beginning because I find that one of the problems that people have at A-level chemistry is that they haven't got solid foundations from which to build more and more complex ideas. So let's start with what we knew at GCSE. So at GCSE, we defined acids as substances with an ability to donate a hydrogen ion during the reaction. Essentially, this was a definition proposed by the Swedish chemist Svante Arrhenius at the end of the 19th century. So an acid, a substance that dissociates or ionizes in water to give hydrogen ions and an anion, and bases, substances that dissociate or ionize in water to give hydroxide ions and a cation. So we could have a look at a couple of classic examples. That of an acid, we're all familiar with hydrochloric acid. So in aqueous solution, it ionizes or dissociates. Either term is acceptable, and I tend to use them interchangeably, to form hydrogen ions and chloride ions. Classic definition of an acid. Our common alkali or base that we came across at GCSE, sodium hydroxide, similarly in aqueous solution, will dissociate to form sodium ions and hydroxide ions. And I'm hoping that we can see that our sodium ion and our chloride ion, so our anion and our cation, are both spectator ions. So when we look at any sort of neutralization reaction via this definition, we are looking at a hydrogen ion from one substance reacting with a hydroxide ion from a second substance to form water. And that was our ionic equation that we should have come across at GCSE for neutralization. Now, this particular definition turns out to be rather limiting because there are a whole number of bases, some of which you'll be really familiar with, that don't actually produce hydroxide ions, but they're still able to neutralize acids in solution. So I'm thinking of things like calcium carbonate, magnesium oxide, so metal carbonates, metal oxides. They do not produce hydroxide ions, and yet they are still quite clearly bases. They are able to neutralize acids to produce salt and water, or salt carbon dioxide and water. In 1923, two chemists, Johann Bronsted and Bronsted-Lowry, both working independently, proposed that since a hydrogen ion was technically just a proton, so let's double check we understand that. So hydrogen, it has one proton and it has a single electron. So when we form the hydrogen ion, H+, and we lose that electron, technically all that we have left is just a single proton in the nucleus. So since a hydrogen ion is a proton, we could redefine acids as proton donors and bases as proton acceptors. And during an acid-base reaction, then, we have one substance donating a proton to another. The acid donates a proton to a base. So if we go back to the reaction perhaps between magnesium oxide and hydrochloric acid, in this reaction we are going to form magnesium chloride and water. In this particular reaction, we can see, let's just balance that up, that the acid is donating protons to magnesium oxide, and that's how we form water and our salt neutralization reaction. So the acid is behaving as an acid, and this use of the word behave is really useful here. The acid is behaving as an acid because it is donating protons to magnesium oxide. Magnesium oxide is behaving as a base because it's accepting those protons. So let's take a couple of minutes to consider more carefully the nature of this hydrogen ion we have in solution, or this proton. This hydrogen ion, this proton has a diameter of around about 10 to the minus 15 meters, which is 100,000 times smaller than the next biggest cation, the lithium cation, which means it has an incredibly high charge density. So a very, very small ion relative to the amount of charge. This means that we are never going to find a proton floating about in water as a free H plus ion or free proton. It is always going to be bonded to a water molecule. So if we take a hydrogen ion, what we're essentially saying, it's always essentially reacted with water to form this person here, H3O+, which is sometimes called the oxonium ion, ion. Sometimes it is called a hydronium ion. And some syllabuses go further and call it the hydroxonium ion. So you need to go back to your syllabus, go back to your textbooks and find which is the preferred name for that particular ion. What does that look like in terms of its bonding? Well, we know that water has a bent shape. So we can draw it like so. Oxygen has 2 lone pairs of electrons, and it uses one of those to make a dative covalent bond to the hydrogen ion. Remember, the hydrogen ion doesn't have any electrons, and then the whole of that is positively charged. So that charge is now spread out over the whole ion. Now, H3O+, again, still has a pretty high charge density, and in solution, like all positive cations, it is going to be hydrated. So if I were to redraw that, you are going to have to bear with me with my slightly dodgy, actually very dodgy artistic skills here. So we've now got 4 areas of electron density around that oxygen, so the shape has changed, which is why I've drawn it like so. Positive charge there. And we are going to have other water molecules from the solution attracted to the positive charge. So essentially we are forming a series of ion dipole bonds between the water molecules and the oxonium ion. We've essentially formed a hydration shell around our oxonium ion. And this is the nature of an acidic solution, where we often see at GCSE H plus aqueous. What we actually are looking at is the H3O in a kind of complex, is a good way to look at it, with 3 other water molecules, all with a positive charge. And then this little person here is going to be further surrounded by a second shell of water molecules. Now, this is a dynamic situation. The attraction, although it's a strong attraction between the water molecules and the oxonium ion, it's not like an ionic or covalent bond. The water molecules are switching places all the times. We could say that there's a dynamic equilibrium going on here. And so we represent all that with the state symbol AQ, aqueous, as in dissolved in water. Now, it's worth bearing all that in mind when we're talking about hydrogen ions or H3O+, H3O+, H+, are completely interchangeable now. And quite often I will be showing you equations using H3O+ because it makes more sense. Often we will be simplifying it down to H+, particularly when we get around to looking at the calculation side of things. The other really cool thing about water is that when we dissolve substances in water, water itself can act as either an acid or a base. Let me give you a couple of examples. So if we take water and we dissolve in it ammonia, we set up an equilibrium where we form the ammonium ion, and and a hydroxide ion. In this particular case, we have water behaving as an acid because it has donated a proton to the ammonia molecule. Hence NH3 becomes NH4+. Ammonia, on the other hand, is behaving as a base because it accepts a proton during this reaction. If we take water and dissolve hydrochloric acid, HCl, hydrogen chloride in it, we are going to have the HCl is the stronger acid, so it is going to behave as an acid, and it is going to donate a proton to water, in which case water is now behaving as a base. Note the use of my language here. So water accepts a proton, hence it is behaving as a base, and the hydrochloric acid is behaving as an acid because it is donating a proton during this reaction. Hydrochloric acid is the stronger acid, which is why water is behaving as a base in this particular case. If this has been useful, hit the subscribe button, the effortless way to support your studies. And by clicking the link in the description below, it'll take you straight to Crunch Chemistry School, where you can access my free math skills course, complete tuition, and worksheets designed specifically to build your confidence and stretch you. Together we can do this.